presenter is Andy Grant from Google ATOS, talking about HPC and deep learning as a service.
So this will very much follow on from Neil's talk and cover some of the same points. So I'm Andy Grant, head of the HPC and Big Data team for Bull in the UK, and as Peter mentioned, we're a full partner in Biomedicine. So I'm going to cover a brief introduction to who we are, because not everybody knows ATOS, talk about HPC and deep learning as a service, and specifically how we're going to do that, how we do it already, but also the work we will do with Hartree. And I've adjusted my talk a little bit this morning to cover big data workflows as well, because that's been touched on a number of times. And then, if we get to it, we'll talk about what we're doing around security as well. So ATOS is a roughly $12 billion company, global organisation, 100,000 employees, but European-based. Very much our DNA is European. ATOS acquired Bull 2 years ago to head up its HPC function. And so it's the largest European IT services organisation and the largest IT manufacturer in Europe. And in the HPC space, we have a range of kind of offers and services that I won't dig into, but just to say there's a broad portfolio from systems through consulting, etc. So high performance computing as a service, there's been a very interesting discussion this morning, and a lot of the points that I raise on this slide I think have been drawn out through some of those discussions. Why is it an attractive option? Well, the little bar chart at the top there is perhaps an exaggeration of a typical environment where a site will have a certain capacity, and at some times of the day, sometimes of the month or whatever, you need more resources than you have available, and therefore you've got an unmet need. At other times, you've got more resources than you need, perhaps over the weekend, and so you've got wasted resources. So the whole HPC as a service, if you like, paradigm is to try and move away from that. The other aspect is total cost of ownership, and particularly when governments keep changing the rules on how funding for CapEx and OpEx is handled, the two things are never aligned. You end up with a complete mess. You can never get the people to support the systems at the same time as you can buy the machines, etc. And you've always got depreciating assets. And we talked on data center energy efficiency. HPC systems, particularly larger ones, can take hundreds of thousands of pounds to power and cool. And then aspects of how do you manage distributed teams, distributed projects, etc. So HPC as a service intends to address those issues. And benefits, increased agility, generally increased runtime, increased return on investment, and increased security. I think the fear a few years ago was cloud. How can I trust? How do I know where my data is? How can I trust that it won't be hacked, etc. And as I mentioned this morning, some very large international, very high-profile projects, such as the Olympics, are now running entirely in the cloud. But all of these arguments could be used as general arguments for why cloud is a good idea. On the other hand, my view is general purpose clouds generally do not work for HPC workflows. Why? Well, at scale, typically HPC is around performance, around trying to get the most out of the system, so you need to be close to the metal in the sense of you don't want layers of software getting in the way. Large-scale HPC systems such as Archer, or our own systems, the team spend an awful lot of time optimizing the operating system. So you don't get a daemon popping up now and then, which just screws all your results. HPC applications often need to bypass the OS kernel to be able to scale. Certainly to scale to hundreds of thousands of cores, this is a critical thing. Often, HPC, you need tuned hardware, so that might be accelerators, or it may just be you need access to large shared memory, which typically you're not going to find in a general purpose cloud environment. Parallel file systems, critical for performance, as we've heard a number of times. And batch scheduling. again, we've heard a number of times, to manage workflows. So these are all reasons why general purpose clouds, and I take the point that not all clouds are the same, and there are HPC elements of some general purpose clouds, but a lowest common denominator approach to cloud adoption generally will not work for HPC, in my view. So how can you get the benefits of a cloud for HPC without some of those drawbacks? Dedicated HPC as a service offerings. So our solution is a thing called Extreme Factory. The idea behind Extreme Factory is to make access to HPC systems easier for non-expert users, but also not restrict it to non-expert users. Expert users certainly access the systems as well. And do that via easy-to-use portals. In this case, it's a thing called Extreme Computing Studio XCS. And also to enable remote visualization, critical part of the HPC process, to be able to visualize your results. And key point here is keeping the visualization aspects close to the point at which the data is generated, so you're not moving vast quantities of data. So we have machines dedicated to Extreme Factory, but let me just explain essentially how it works. A user will go to the portal, they could use their own local facility, which we call Extreme Factory Private, or they could go to either one of our computing centers or a private center somewhere that's offering Extreme Factory as a private cloud service, or a pay-as-you-go public cloud service. And the portal, this is the key bit, because this is where authentication, job management, license management for the applications, etc., all happens. So this is the crucial bit where you interact with the service. And there's a combination here of bespoke software development, which is typically open source, but also third-party applications. Somebody mentioned ANSYS this morning, for example. So how do you integrate those third-party applications? The picture here shows what a session might look like. So the front window here is what the portal would look like. You access that and you click on one of the buttons, which would bring up the list of applications. So the window on the left is showing for this particular user what applications they have available to them. So they clicked on an application and it will bring up a job submission form. That job submission form you could expose or you can hide as many parameters as you want. So if you want the ability for non-expert users to be able to run an AMD job, upload data file, how many processes do I need, press go. If you want a more expert user, then you would have more parameters exposed. And you can do this based on user class. So if me as a non-expert were to log on to this, then I'd want the minimum perhaps. Once the job's submitted, you can then monitor what's going on the system. And we've got a vast quantity of applications that are already portalized, if that's such a word, that are available within the portal. And these range from many ISV codes such as ANSYS, LS9, etc., of the automotive industry perhaps, to molecular modeling codes, life sciences codes. And typically it would take half a day to create a portal sheet for submitting another application into that. And then we get on to visualization. So your job is now running on the remote facility, you've uploaded your data file, away you go. You want to see the results. The one thing you absolutely don't want to do is generate a big data file on the remote system and then have to pull the whole lot back to visualize it locally, because the cost of transferring data will be too high generally. So it's important that the visualization is co-located with the HPC resource, which is co-located with your data. So run the visualization, attach it to the job, and then all you're sending back to your local system is a stream of pixels. So you're sending mouse movements and control and rotation commands, etc., to the system, coming back as a stream of pixels, which is very secure. Like, nobody's getting access to your data. The maximum they could see is a snapshot of a stream of pixels. And by the way, you're sending it back over an encrypted tunnel. So actually, it would be very hard for the human to do that. Your intellectual property is therefore protected. Now, we have, maybe the next slide. So, one of the things we offer is the ability to tailor this portal. So there are a large number of companies who will take what we've got and tailor it for their own private cloud. So here's one example of a company, EXA, who do CFD modeling, who do exactly that on their own private cloud. So you could imagine Biomed having its own private cloud in this case. And we have a large number of customers doing it in different ways. Perhaps one of the biggest known ones is Renault. So Renault do all their crash simulation and all their finite element work using this mode. BMW, I mentioned earlier, are a new addition to this list, doing similar kind of work. So what are we doing with Hartree? Well, my view is that it's important that we make available the resources that have been publicly funded, particularly for industrial engagement, available to the broader community and to projects such as Biomed. So Hartree, through a recent procurement, have just bought a large supercomputer from us called Sequana. The details of it here. So 3.4 petaflops. It has a large number of regular x86 Xeon nodes. It has a very large number of Knights Landing nodes. It has large memory nodes, etc. So you can imagine a scenario where you submit your jobs via Extreme Factory to a specific queue. So you've got you're doing some pre-processing where you need large shared memory, for example. So you submit to a queue which targets those high memory nodes. Or you want just the maximum compute you can get, the maximum number of cores, so you submit to the Knights Landing queue, for example. So we will be putting the Extreme Factory software on this Starfelt Pike system and offering that as a service both to the academic community and to industrial collaborators, partners, etc., as part of the overall industrial engagement. And some of that will be resource that's freely provided, and some of it will be paid for, because the system ultimately has to become self-sustaining. And Neil mentioned deep learning, the JADE system. So this is a collaboration between ourselves, Oxford, and Hartree to host a national deep learning service based on NVIDIA GPUs. So in this case, it's 168 Pascal GPUs. So I'm not sure how that translates into GPU cores, but a very large number. And a key thing here is these GPUs are 8 GPUs per block of memory. So they're fat GPU nodes. And the first family of GPUs to be connected via NVLink, which is the NVIDIA high-performance interconnect between the GPUs. So that system is currently being installed at the moment. It should be going live very soon and offered out as a service. And the intention is, in the fullness of time, that will also sit behind the Extreme Factory portal as well. So you would have a queue that you submit to the GPU nodes. And for those of you who aren't familiar with deep learning, and I'm thinking Anna here, the problem you described earlier. So deep learning is an artificial intelligence technique using deep neural networks, where you have a system that is trained over time. The example I use quite a lot is mammography scans. So it's a very mundane human task to scroll through lots of images trying to spot something that's a very small feature in a very fuzzy image. If you can teach a system to do that and get the accuracy higher than a human, then it becomes a much more productive task and a much better use of the human resource. So you could train the system with thousands of mammography scans to spot where a tumour exists. Once you've done that training set, which is a real HPC problem, then the next stage could be, okay, take my latest patient, scan them against the reference data set. Do I have a match? If so, look for further analysis. So it's those kinds of problems that we're looking for with the deep learning system, and ultimately with the intention that this will become part of regular medical care. Okay. So that's the HPC Deep Learning as a Service. The other bit I just wanted to mention, because it's come up a number of times this morning, is around workflows and big data workflows. Now, anybody who is in the big data space knows it's the thing of the moment, and every week some new technology pops up. This was a snapshot from last year of the big data technologies. So how, as a researcher, are you to make anything of this? So what we tried to do is filter out what we believe to be best of breed components within each of those different areas. Our data scientists will work with the different organizations to say, okay, well, we know there's a class of batch issues, we know there's a class of analytics, etc. So we'll take those best components and we put them into a service catalog. So a service catalog that then becomes available to a researcher or an end user or a developer to create a big data application. So if you've got an application where you need to ingest data from a streaming system or from an MRI scanner, you need to do some analytics on it, you need to combine it with some other data, and then you need to visualize it, then you can plug together the appropriate components from the service catalog to create your big data application. And this is all open source, by the way. And then up here, somewhere, there'll be a button that says deploy. And then you can deploy that on Azure, on Amazon, on our cloud, or on-premise. Now, the neat thing here is not all of these components need to run on the same machine. So if you imagine that you want to combine genomic data that's coming from sequencing machines with the phenotype data that's contained within a patient's electronic health record, combine that to look for any contraindications to their treatment. So you might have, as part of this, a genome sequencing pipeline that's running optimized on a GPU cluster. Goes off, runs there, the data is brought back into the framework, and it's combined, and then hopefully you get some improved diagnosis over time. So that's one of the things we're working on, is how we can embed some of those different components into the framework. Okay. So let's just go through that. One of the other aspects of our involvement in the project is around application optimization and some of the higher value services. So as well as the cloud layer that I mentioned there, our team have involvement in terms of application optimization. So can you optimize for I/O? Can you put your application to GPU, etc., etc. So there are allocations of time from our Center of Excellence in Parallel Programming to help with that activity. And on the right-hand side there, all within a framework of security. And so CPP have resources dedicated in the project to help you do this. And if it's a case of how do I take my 1,000-node application and get it going to 10,000 nodes, or how do I reduce my runtime from 6 hours to 2 hours, hopefully we can help with those problems. Because we have people with expertise in each of these different domains. So I'm probably at the end of my time, so I won't talk about security. But if you are interested in any of these aspects, please feel free to get in touch and I'll explain more happily. And apologies if I talked very quickly there. I had more to get through than I should have, than the time allocated. Apologies.